Okay. Well, thanks for coming. We've been working on, so the talk, the paper that this talk is based on, we worked on for quite a while. So it's nice to be able to kind of share results from this. And the main topic of the paper and so of this talk is how we, when we use neural networks, particularly in the physical sciences, how do we sort of interact with the information that gets learned by things like neural networks? And essentially what I want to walk us through is an interesting problem where this crops up and how we can kind of learn interesting physics from machine learning. So to start off with, this is sort of our list of collaborators. So myself and my advisor at UC-Irvine is Daniel Whiteson. And then we also are working with Jesse Thaler at MIT, who's sort of our contact for most theory questions. And then kind of jokingly, the machines are a little bit of our collaborators, because that's essentially the topic of the paper is that we want to communicate information with them, or rather from them, and from what is learned from the machines. So I think the best way to start out is to define or introduce kind of an interesting machine learning black box learning problem that we encounter specifically in high energy physics, and explain or show how this kind of motivated our approach to learning from the machine. So as I'm sure most people are aware, we generate really large data sets, especially in high energy physics. According to CERN, in their 4 biggest experiments, so ATLAS, LHCb, CMS, and ALICE, they generate something like 25 gigabytes per second of sort of raw data when it's running. And so obviously we end up using a lot of sort of big data analysis techniques for all of this data. And we don't just use it for sort of your like bread and butter, what you'd expect that machine learning is good for, things like classification, but you'll also see it sort of built into a lot, sort of through the entire pipeline of detector research. So from triggering and classification to data pre-processing before you do any analysis. And if you look on the archive, what you'll see is there's about 1,000 specifically high energy machine learning papers uploaded roughly every month. So this is a very big kind of booming area of research in high energy. One of the problems, though, and kind of the central problem that we try to address, is that most of these machine learning tools that we end up using are what gets called black box methods. So you have this large data set, you give it to something like a neural net or a deep neural net with a task, something like jet classification is the one we end up looking at. And what you end up getting out is these predictions with the data, but you don't really know how the whatever machine learning method you used solved the problem. So you can't sort of crack open the black box and get out a function that tells you how those decisions were made. It can't tell you what aspect of the data it found useful or not useful. And that's the kind of thing that we would be interested in. But you might ask the question, well, so why is that a problem? Why can't we just use like a black box method to give us these predictions, even if we don't know how it's giving those predictions or how it's making those decisions? And so the example that I'm going to give where I think this is an interesting problem that we get from a black box is in the area of jet classification. So a jet you probably are familiar with as when you collide protons, you produce these sort of free quarks and gluons, and those quarks and gluons then hadronize into these collimated jets or sprays of particles. And we can detect those in, say, like a calorimeter in the detector. And usually that'll start out as this really high dimensional, low level data set. And then we take that data set and we kind of pass it through a bunch of levels of dimensionality reduction. So you'll kind of reduce your data set and do reconstruction and then select out subsets of the data that are interesting. And ultimately, you'll end up a lot of times with these sort of high levels, simple 1D physics variables, which is where you get all of your histograms from. So in the case of jets, there's two kind of common, very low dimensional or lowest dimensional versions of a jet. So one that's sort of common is you can take the sort of the transverse energy that you get in your calorimeter, and because that's sort of divided up in eta and phi space, you can kind of treat the energy depositions in your calorimeter almost like it's an image. And so if you can treat it like it's an image with pixels rather than transverse energy, then you can start applying these image, like computer vision techniques. So a convolutional neural net, for example, is a common computer vision method on images. Even lower dimension than that, though, and another common way to sort of parameterize a jet is with these really simple 1D jet substructure variables. And these tend to be physics motivated. So things like jet mass, or rather the invariant mass, the jet PT, and then there's some slightly more exotic ones that are tailored to specific problems like n sub jettiness, which is a useful tool for classifying different sort of multi-prong jets. And an interesting question that we asked in a previous paper was, which version of this data actually works better? So the high level is sort of very physics motivated, whereas the low level jet image is kind of just the raw calorimeter information. And so it's an interesting question of, well, what works better, these physics motivated 1D observables or a jet image? And the specific task that we asked it, that we wanted to do this comparison with was a monojet dijet example. But specifically a dijet from a boosted W boson. And the interesting thing about a boosted W boson is that when it decays into two jets, they end up, if it's high enough momentum, they end up getting collimated and sort of overlapping. And so what ends up happening is, even though you have two jets, the overlapping causes those two jets to sort of look like a single background monojet example. And so this is kind of an interesting jet classification task of signal versus background, where you ask the question, well, can a convolutional neural net looking at jet images, can it figure out the difference between a monojet and a boosted dijet? And then we can compare that to sort of jet substructure. And when we ask this question, what we essentially find is that the jet image version of the data works better. If you try to take your data set and try to reduce it to sort of the simplest 1D version, it doesn't perform quite as well as if you just give, say, a convolutional neural net these raw jet images that are just calorimeter readings. But because we've used a black box, what ends up happening is that information, whatever additional information you have in the jet image is sort of inaccessible. So you can't really ask the convolutional neural net what it learned or what it's doing that's benefiting it above and beyond the physics observables. And so it's kind of trapped and locked in to this black box. And beyond that, so you sort of lose out on this information that you don't know the physics that it's using to learn that. You also, there's complications in using these sort of higher dimensional, low-level data sets. So one being that you can't really validate your data set very easily. In the case of something like invariant mass or PT, you can take your sort of histograms and you can look for either oddities in the way that your distribution's laid out, and you can make cuts to sort of deal with that. And each of the different high-level observables are you can inspect them one by one and study them individually. So that's just something you can't do with high-dimensional data sets. Another one is you can't really study the systematic uncertainties or quantify the systematic uncertainties of a low-level data set or of a convolutional neural net. whereas that's something you can do with a high-level observable. You can apply what you know about the physics of, say, invariant mass, and you can quantify the systematic uncertainties and then compensate for that in future studies. And then there's also lots of little, well, not necessarily little, but pragmatic problems. So something like a low-level data set is just much more storage intensive. It takes a lot more training, a lot more memory to use. You can't do, for example, if you wanted to do in-time machine learning, that suddenly becomes a problem if your data sets are too big or too complex or take too much time to learn from, because the problem it's trying to solve is much more complicated in this other format. But really, I think the more interesting one is just you're missing out on this physics information, and you know it exists because somehow the low-level convolutional neural net learned it, but it just doesn't exist in your physics variables, and you'd like to know what that is, and maybe even learn what you're missing from the physics. And on top of that, this isn't an uncommon problem. So we have a few different papers on arXiv where you see this sort of low-level, high-level version. So in the previous example, we had the low level was convolutional neural nets on jet images, and the high level was things like invariant mass or n sub jettiness. Well, here, this is an example of a Higgs classifier. And again, there's a low-level way to view the data, which is sort of all the different jet PTs of the different constituents and things like the missing transverse energy. And then there's a high level, and it's mostly invariant masses of the produced outcomes from the decay. And what you find is, again, there's this big gap between the low-level kind of kinematics view of the problem and the high-level physics-motivated parameterized version. Or there's another paper we just finished where we do a similar kind of jet image analysis, but for electron classification. And in this case, we look at not just the, we look at jet images both in the electron calorimeter and the hadronic calorimeter, and compare this to sort of a standard set of high-level jet observables for electron classification, and it's the same thing. You get this big gap in between the low-level and the high-level version. So it's common to lose information when you try to use your physics knowledge to reduce the data set. So that's kind of the problem. And then what are the ways that we can solve this problem? So there's essentially three different ways you can approach the problem. The first is just to avoid using these black box solutions. And that's kind of not ideal for the really obvious reason that you just can't take advantage of any of the power of something like a deep neural net. So you have this powerful tool at your disposal, but you just don't want to use it because you're not necessarily sure you can trust the results, or you think you're not sure that what it's learning is necessarily physical. The second one that's a bit more common recently is to come up with some kind of modified black box method. And then when you feed your data through, some part of this modified black box is interpretable, and then you can understand what it's doing in kind of this subspace. And there's an interesting paper from Microsoft Research where they apply this kind of approach to sort of healthcare applications. The third approach is the one that we're suggesting in this paper, which is use your black box, so something like a deep neural net or a convolutional neural net in our case, and then map the result that you get from that into a space that's sort of human readable and interpretable. And the advantages of this are that, one, you sort of get the full performance that you would get from whatever machine learning black box method you want. So you don't have to give up the good performance of say, the convolutional neural net on jet images. And the other convenient aspect of this is that you're not sort of restricted in only using a specific type of machine learning. So the Microsoft Research one, you're sort of stuck using their version of, it's sort of a deep neural net combined with a generalized additive model. In our version, you can choose whatever you want, and then whatever solution it comes up with, you then map into something that's readable. So this is kind of a little cartoon describing the approach that we take. So there's 3 components that you really need. The first is some kind of low-level solution where you think that there's extra information that's being learned. And this is the information that we're going to try to map into a human readable space. So for us, this is a convolutional neural net on jet images. The second thing is a space of information where the information that you don't have, that you're sort of missing, where it might exist. So, so for us, this is going to be energy flow polynomials, and I'll explain that in a second. And then the third component is a high-level version, a metric that's going to help us map this missing information from the low level into this space of high-level observables. So like I said, the first aspect of this we already have. This is the low-level CNN on jet images. The second component is the human engineer, or the human interpretable space. So one of the reasons that we are collaborating with Jesse Thaler from MIT is, so they have this nice paper where they present a complete basis of jet substructure, so these energy flow polynomials, there is an infinite set of jet substructure that in principle should, if the information exists as a simple 1D jet substructure observable, should exist as one of these energy flow polynomials. And the way that they're sort of defined is any isomorphic graph that you can construct where the nodes of your graph are these sums over the fraction of momentum of your constituents, and the edges of your graphs are the angular separation of those constituents. And so any of the infinite graphs you can construct with these as your components is a member of this energy flow polynomial set, and is sort of a candidate for a jet substructure observable that might be the sort of missing information. And in addition to these graphs, there's a kappa and beta parameter. So you can kind of give emphasis to either the momentum component of your constituents, or in the case of beta, the angular separation of the constituents. So there's sort of simple versions of the graphs where for 2 nodes and a single edge, you're multiplying 2 components of momentum and just the angular separation between them, up to these really complex sort of multi-node graphs. And all the jet substructure observables that we're familiar with, so things like invariant mass or energy correlation, kind of exist in this infinite space of energy flow polynomials. And then the third piece, once we have the low level and then this candidate space of high level variables, is some way to kind of map between them, some metric that tells us if we find some new information, where in the energy flow polynomial space does it exist? And in the beginning, we kind of thought, well, maybe it's sufficient to look at something like a ROC curve. So a ROC curve will tell you, with say a neural network, how well does your neural network do at classifying your signal and background, say in a binary classification problem. But what we realized is that essentially a ROC curve will tell you how well that a certain neural network is performing, but it won't really tell you whether or not 2 neural networks are performing a task in the same way. So you might, for example, train a neural network on low-level data, and then train a neural network on high-level data, and you might get the same or similar ROC curve, and the area under the curve being the same, but that doesn't really tell you that those 2 neural networks are making the same choices, or that they're solving the problem the same way. So what we ended up having to do is to come up with our own custom metric that's based roughly on the way a ROC curve works, but rather than using, so in the case of a ROC curve, what you're really doing is you're looking at your false positive rate, and at all of these sort of thresholds of false positive, you're asking the question, what is the your true positive rate at that point. And then you're plotting out how your true positive depends on this threshold of false positives. And so for our task, what we really want to know is for these two neural networks that are trying to make the same predictions and trying to learn the same information, for all the different outcomes that it can come up with, what is the decision making, or rather the decision surface of those two neural networks? And are they making the same decision at each of those kind of outcomes, or are they making different decisions? And so we came up with this metric that we call the decision ordering. And the way you can think about it is, so say you have a pair of inputs, a signal and a background. Essentially what you can ask is, do those two neural networks map your signal and your background in the same way, or do they map them in the opposite way? So one neural network, for example, might map the signal as a signal point and the background as background, so it's making the correct prediction. Whereas your other neural network might make the opposite choice. It might take your signal input and think it's a background and make a prediction that's incorrect. And so what you can do is you can kind of Monte Carlo take all these many millions of signal background pairs and ask whether or not your two neural networks are making the same choices or opposite choices. So do they take all the same signals and correctly map them to signals, or do they take them, does one take a signal to signal and the other one takes a signal and maps it to a background? And if you can do that, then you can sort of just take an average of all of these mappings and ask how often on average do these two neural networks either make the same decisions or do they make opposite decisions about the way that your signals and backgrounds should be ordered. And in effect, what we're doing then is we're taking slices through this decision space, and we're asking for our two neural networks, are they making the same decisions or opposite decisions on average at all of these different slices? So we apply this kind of metric, and what I've sort of described and what we expected is what you end up seeing. So up here on the top right is all of these AUCs. So you're taking a ROC curve for these high-level observables. And so each of these high-level observables has some sort of individual performance at how good a job it does at separating out these monojet, dijet examples. But what you end up finding is that the amount, how good a certain input is at being, say, a classifying feature is not the same thing as asking the question of how well does two neural networks make a decision using that as an input. And so an interesting comparison is, say, these energy correlation functions. So C2B1 and C2B2 are very similar jet observables. And you can see when you look at their ADO that they end up making very similar choices for a lot of the signal and background pairs. But if you look at their AUCs, the C2B1 and C2B2 end up making very different, they have very different performance with those observables. So what you end up finding is that how well a feature does at making a classification when given to a neural network is not the same thing as how well a neural network, or how similar a neural network is making decisions with, say, one observable versus another. And what you also find is that the traditional jet substructure observables are not these sort of orthogonal functions. There's a lot of overlap. So a lot of the information that you capture, say with jet mass, you're sort of double counting or you're capturing with energy correlation. Whereas something like n sub jettiness is very distinct from the jet mass, or the invariant jet mass. So these are the three pieces and these are the only three pieces really you need to try to do then the algorithm we use to try to map the missing information from the low level into kind of this high level space. And this slide I hope gives a simplified version of what our algorithm is, where we try to sort of iteratively build up this, this new energy flow polynomial as a best choice of a jet substructure observable. So we have our low-level jet image neural network. We have these high-level observables like invariant mass and subjettiness, and we have this pool of candidate high-level observables. So the first step in our algorithm is just to train a neural network with the with the high-level jet substructure. So things like invariant mass. So these are all the things that we want to be compared to the low level. And from the output of your deep neural net on high level, we generate this randomized set of signal and background pairs. And so these are going to be signal and background pairs that we want to ask about the mapping between signal and background. And we want to check essentially whether or not the low level and the high level are making similar or opposite orderings. And once we've established which signal and background pairs are making the same orderings and are making different orderings, we want to isolate just the subset where the low level and the high level are making different choices. So in this subspace, the low level convolutional neural net and the deep neural net on high level jet substructure, they're making the opposite choices. And so we call this our differently ordered subset. And once we have this differently ordered subset, we can essentially ask the question, well, which EFP does the best job of filling in the information in this differently ordered subset? So in the space where the high level and the low level disagree, which EFP agrees with the low level most often? And this new EFP that makes that the same choices as the low level, we want to include that as a new high level, and then retrain our high level, including that EFP. And so once we go through the algorithm a second time, now you've included a new EFP that fills in that information, and you can ask the question again, well, now with the high level and this new EFP, where does the high level and the low level make different choices? And you kind of iterate this process over and over until you've filled the gap, essentially. So in terms of the logic, I think I've explained it in the previous slide, but this is kind of a cartoon example of what we're trying to accomplish. So you start off with this high level and low level space where you're making a lot of the same choices. So say in this upper space or lower space, but there's this differently ordered subset where the high level and the low level, so the blue and the red, make very different decisions about what to do with these signal background pairs. And so what you do is you isolate those signal background pairs in this differently ordered subspace, and then you find just what is the EFP, this green line, that is very similar to the low level. And so when you give the high level neural network that EFP, that neural network can reach for that EFP in this sort of differently ordered subspace to kind of compensate for the fact that the other high level do a poor job of giving information in that space. And then, so these curves would all end up then, I guess, changing when you've included that EFP, but then you would just repeat the process and try to find the new differently ordered space. So we tried this, this algorithm on the problem of this monojet and boosted dijet problem. And we started out with our 6 high level, so those being invariant jet mass and subjettiness and a few energy correlation. And so you can ask the question, well, how many times do I have to iterate through this algorithm in order to get kind of useful physics information? And it turns out for this case, you just need to do it one time. On the very first pass, you pick out an EFP. So this EFP up here is the one that the algorithm chose. And when you include that back in as a new high-level observable, you end up with the same performance, the same AUC rather, as the CNN. So you just need to add in this one extra EFP. But what you also see is that the ADO value is not equal to 1. So it's performing as well as the CNN, but it's not necessarily making exactly the same choices as the CNN in all respects, which is interesting because essentially what we found is a deep neural net or a JET substructure version that performs as well as the CNN, but is now interpretable, but still makes some different choices than the CNN. In terms of the specific EFP it shows, there's you can kind of interpret now what does that EFP tell us. So one of the things that's interesting is a property of energy flow polynomials is any energy flow polynomial where the kappa parameter is not equal to 1 is not infrared or collinear safe. So which is not true of all the other JET substructures. So in general, we try to choose JET substructure observables that are infrared and collinear safe because you can't necessarily know whether or not, for example, soft emissions or like collinear splitting is going to affect your results. So it's convenient if your high level variable is IRC safe. And the specific one it picked is not IRC safe. So for example, a CNN might be benefiting from not having that restraint or that restriction put on it. The beta equals half parameter. So because the beta is the angular resolution parameter, the fact that it's a small value essentially tells you that it's preferring these sort of small, observables that probe small angle behavior. So it could be, for example, that the CNN is benefiting from looking at smaller resolution information rather than whereas the other jet substructure observables are not sort of these small angle. And it also, the energy flow polynomials have another feature, which is the graph, the chromatic number of the graph tells you useful information about how many prongs it's probing. So it has this feature that the chromatic number -1 is, that graph is then sensitive to that number of prongs. So a chromatic number 3 graph is sensitive to a 2-prong jet image, or if it was a chromatic 2 graph. So the fact that it's chromatic number 3 essentially tells you that the EFP it selected is kind of sensitive to the fact that it's a dijet problem rather than, say, a monojet. And then the histogram at the bottom, this is the distribution for that energy flow polynomial. On the left is just this EFP, and on the right, so this is after you just look at the differently ordered subspace. So it's kind of interesting if you just look at the area where the low level and high level make different decisions. It kind of makes sense why they make different decisions, because there's very little signal background separation in this space. So it kind of makes sense that it's difficult for them to decide in this space what the correct answer is. So this is kind of already an interesting result, that we can recover a useful physics interpretable variable. So we had a kind of a secondary question, which is, well, if it can work with our existing high level, what if we don't give it the observables that we already know about? And we just sort of started off with the minimum set of information and ask the algorithm to pick EFPs for us. And could we recover the low level performance? And would those EFPs that it picks be similar to the ones that we already use? So things like invariant mass, or would it be very different? So this slide shows that search. So we call it the black box guide. So we're in every step, we're asking the sort of black box deep neural net to always pick a new EFP and using kind of the bare minimum high level. So we start off with just the jet mass and PT. And the PT is only there really as a scale for the EFPs. So that it's easier for the neural network to understand how big or small the EFPs are if it has jet PT as kind of the scaling factor. And what you essentially find is, so each time it goes through the process, it picks a new EFP, and each time that EFP improves the AUC or the classification performance. And ultimately, you do end up recovering the low level performance, and you do it with 7 EFPs, which is maybe 1 or 2 more than we needed for the previous example. So with MJET, with JetMass, PT, and 7 EFPs, we have roughly the same number of high-level observables that we had in the previous example where we used our existing information. But it ends up being really interesting because the EFPs that this process picks is very unconventional or very out of the norm of what we would think to pick based on kind of physics motivations. So these are the first 4 of those graphs. And we can break down what information is kind of contained in these EFPs. So the first EFP is this much more complicated graph. It's a kappa equals 2 graph. So it's another one of these infrared collinear unsafe graphs that we probably wouldn't normally pick. It's a chromatic number 2 graph. So like I said, the chromatic number -1 tells you how many prongs it's sensitive to. So because it's chromatic number 2, it's essentially sensitive to 1 prong jet substructure, this is the same as jet mass, which is interesting because jet mass was already in that information. So it ended up picking that despite the fact that jet mass is kind of giving that information to us. But unlike jet mass, whereas jet mass is a graph that has 2 nodes in it. So like I said, the jet substructure observables we already use exist in the EFP space. Jet mass is a 2-point graph. This is a much more complicated 5-point graph. And also, unlike jet mass, the beta value is another sort of small angle radiation probing EFP. If you go to the second graph, it's another IRC unsafe graph, but now it's in the opposite direction. So now it's the kappa value is very low, or rather it's 0 in this case. It's another chromatic number 2 graph. So again, it's picking an EFP that's sort of sensitive to monojets rather than dijets. And the fact that it's beta equals 2 means now it's picking an EFP that's sensitive to wide angle radiation. The third graph is also interesting because this is it's a jet substructure observable that we already use. So this is this dot graph is equivalent to jet multiplicity. So it's one that we know about, but it's not one that we were using in our previous data set. So this one's kind of interesting because it's picking a jet substructure observable that we already know about, but that we didn't think to use in our original study. And you can kind of go through each of these graphs one by one and interpret them, but kind of a wider view of it. So of the 7 EFPs it picks, only 2 of those were IRC safe, which again is something you would generally not, something you would kind of not go in choosing that to be the case, but the algorithm chose those things. It's also much more sensitive to 1-prong jet substructure. So all of these chromatic number 2 graphs means that it's much more interested in trying to understand the monojet problem rather than the dijet problem. And in fact, you don't get anything other than monojet sensitive EFPs until the 6th EFP. And at that point, it picks something that's chromatic 4. So now it's suddenly, for some reason, it's sensitive to 3-prong substructure. So it doesn't even sort of look at like the dijet problem directly. It's sort of an indirectly, it's trying to understand monojets instead. But I think the interesting takeaway is that even though you can recover the performance of the low level, it picks graphs that you would sort of not go in choosing on your own. So in addition to these 2 searches, we have some other interesting questions that either we thought of or people kind of posed to us. So one of these is, so the black box guided, this is that search where we're trying to start from the minimum set, so just invariant mass and jet PT, and we want to build up this set of EFPs. So one interesting question is, if the information exists in the EFPs, and you could have just started with the invariant mass, do you really need to do this guided process, or couldn't you just kind of pick EFPs and try a few different ones and work out which EFPs kind of work. So we tried one study that we're calling brute force, where you try essentially every combination of EFP in every pass. So you start out with JetPT and JetMass, and you try those two plus each of the EFPs and just see which EFP kind of works best, and then include that, and then start over and try to include a second EFP and just figure out which combination of those EFPs works until you've saturated. Another interesting question is, well, so this data set is a labeled data set, so you know the signal, you know whether or not it's signal or background. So why not just use kind of the ground truth? Why not use these labels to guide your selections of EFP? Why do you want to train a separate low-level jet image convolutional neural net and then try to match the decision-making of that? And so we call this the truth guided. So you're doing essentially the same iterative process, but rather than letting your CNN, the decision surface of your CNN be your guide, you're letting just the signal and background, the truth labels, be the guide. So we run these other sort of studies through the same 7 passes. And what you end up finding is, in the brute force case, the brute force performs pretty well. In fact, it performs the best, but you kind of expect it to perform the best because you're just trying every combination of EFP. And what I'll show in the next slide is this. So you can sort of do this. It's just extremely inefficient. And if you wanted to expand, for example, your pool of EFPs to include more interesting results, or if you didn't get the results you were hoping for in the first batch, it's just overly complex to try every EFP. And in terms of the truth guided, so this version where we just try to use truth labels, what we end up finding is that you just can't reproduce the performance. So you are unable to reach the low-level jet image version's performance. So in the brute force case, this is the same graph, but now measured by computing time. And what you end up seeing is that although the brute force version works, it takes longer to perform a single choice of EFP with a brute force search than it does to do the entire black box guided approach. So it's just not something you'd really want to do if you can help it, unless I guess you have the resources. And in the truth guided case, so like I said, it ends up not ever managing to reach the low level performance. And if you think about it, this actually makes a lot of sense, because in our algorithm, what we're doing is we're asking the question always, where does the low level and the high level make different decisions? But if you're using the truth guided, or rather the truth labels, there's sort of this upper limit to how much information exists in there that you actually have access to. And so you kind of reach this saturation point at which the low level and the high level disagree about how to map signal and background, but that disagreement is not based on choices in how to optimize the decision surface. They're just disagreements in what the correct signal and background mapping is relative to what the sort of true mapping is. And so you reach this point where the truth is unwilling to be changed because it's the truth labels, and then your algorithm can't really adapt because it can't use the fact that those signal background mappings are different to improve it. Whereas with the black box guided, you've let the convolutional neural net do all the heavy lifting of kind of optimizing the problem, and then you are just trying to optimize a separate network to make the same decisions as that already optimized convolutional neural net. And so you end up benefiting from the convolutional neural net and learning the same information or a similar set of information as it. So as this is kind of my overview conclusion. So one thing that's pretty obvious is that most of these machine learning techniques are only going to become more opaque and become more complex. They're not very likely to become less complex or less opaque. So things like our guided iterative algorithm are the kinds of things we have to start thinking about more if we want to ever overcome this problem of our low-level information outperforming our high level, and then not knowing how to map that into physics information that is meaningful and understandable to us. And in addition, these increasingly complex and opaque black box methods still give the same problem to most physical science motivated machine learning applications. So things like being unable to validate or measure systematic uncertainties of your information. So although our convolutional neural net can do a really good job of making predictions, it's you have to do extra work to map that information into kind of the physical science aspect of that. So in the paper, we kind of conclude that with a suggestion that wherever possible, you should try to use interpretable models. And a lot of those, so things like generalized additive models, they tend to be very powerful. So whenever possible, if you're not getting these, you shouldn't immediately just reach for the deep neural net. But in the scenario where the deep neural net is learning more information, essentially you should make some effort to take that information and map it into a physics motivated or physics readable space. So in our case for jets, we have the energy flow polynomial space, but in other physics scenarios where you have a high level and low level space, you should find some way to essentially map that information into a context that has meaning to us as physicists. So I'm happy to answer any questions or explain anything that I didn't explain well, but that's essentially the conclusion.
Excellent, thanks, Taylor.
Yeah.
So let's do this with the hand raising. Anyone have questions? Michelle.
Hi, thank you so much for that talk. I really enjoyed it. My one question is actually kind of mapping your big picture goals and discussion to the specifics that you talked about, because from what I understood, and maybe I'm wrong, is that with these with this jet problem, you have the energy flow polynomials that created a basis that allowed you to create features that has the potential of matching the performance of your black box model. So if you were to extend this to, say, a different physical problem where you may not have something like that, do you still see this succeeding?
So so it's a good question because in our case, like you said, yeah, we have a very clear space from which we can kind of pick from. In the case where you don't have that, then it's more difficult because you do need some way to sort of parameterize the information in a way that makes sense physically. And so I think this specific algorithm is more difficult if you don't have kind of a proposed theoretical space where the information can exist. But like the example I gave of kind of the Microsoft research paper where they look at interpretable models, so that's a kind of an example of where you don't necessarily need to know ahead of time what your physics space is in order to be able to interpret how the neural network is learning information. But I guess really if you do want to understand what the physics is, I mean, I don't know if there's any way to get around having some kind of interpretable physics space in which that information lives for you to try to understand it with or without this algorithm. I don't know if that quite answers the question, but.
Yeah, that answered my question. Thank you.
Daniel?
Yeah, thanks, Taylor. Really good talk. Is there an argument here that you could use the physics observables or physics, inspired polynomials to improve the performance? I assume using polynomials is much easier on, say, memory and speed, than a big, deep CNN. Is there an argument that you can boost physics polynomials to high enough accuracy, but still get the good trade-off, get speed and memory boost?
So I'm not sure if I understand it entirely. So, I mean, I think that's essentially what we're hoping is true most of the time, is that you don't actually need to, you can get the same performance as the low level in this case without having to sacrifice the interpretability. If what you mean, I guess, is that, so this would be something that would be difficult to do on the fly.
Sure, but this would be like after the fact, right? Once you've found the correct set of EFPs, then you can.
Yeah, so this specific method of learning is once you know that there's more information to be had, and you just don't really know what that information is, this technique will guide you to finding sort of what, in our case, the low level was probably doing to find that information. But it's not necessarily, but yeah, it does, you wouldn't necessarily be able to use it kind of in the way that you could use something like convolutional neural nets, where you can train it and then ask it to make predictions kind of on the fly.
Yeah, right. Okay, thanks.
Kevin.
Hi, yeah. Could you go back to slide 25, please? I think it was slide 25.
Yeah, this one.
Yeah, I found this really interesting, and I'm not sure if I was understanding you correctly, but when you conclude that the choices that were made were unconventional, does that imply somehow that if you combine sort of the conventional choices with these, that you would have even more discriminating power?
So I don't know, it's not something we've looked at, and my intuition is that the fact that these graphs on their own, also the fact that they perform as well as the low level probably means that we've reached kind of the saturation point of how much information you can learn. So I don't think you would see any difference between combining these with the existing high level. But the algorithm is, it's very dependent on, it's always very dependent on the previous choices that were made. So if you start out with, say, the normal jet substructure observables like jet mass and end subjettiness, the specific energy flow polynomials that it'll pick is going to be very different than if you start with, say, jet mass and end subjettiness, because it's always just trying to sort of fill in this gap of information. So most likely these specific choices of EFP on slide 25 are not necessarily helpful in the context of a separate neural network that's trying to use the existing jet substructure.
Okay, and if you'd permit me one more quick follow-up.
Yeah.
Did you try multiple trials of this to see how repeatable it is, the choice of variables? Like if you started with a different randomly initialized CNN, does it converge to the same choices, or does it make different ones?
No, yeah. So one of the things that we do is when we're choosing, for example, these signal background pairs, in order to ask like when the high level and low level are making different decisions, we're very careful to always sort of scramble the signal background pairs. So it's always essentially a different data set, and it's very consistent that it'll pick the same EFPs. Okay. So it seems, yeah, it's pretty kind of invariant to individual details of how you're training the network. It'll pick the same EFPs pretty consistently.
Thanks.
Any other questions? Or just last call. We're just at an hour, so I guess thanks again, Taylor. Really great talk, really interesting.
Thank you.
And bye, everyone. Thanks, Taylor.
Thanks.